Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. Today we're going to discuss feature extraction from real ECG signals. Basically what we're going to do is to use whatever we used last time and basically try to implement the kind of features that we talked about last time basically on ECG signals. Okay? Walaikum salam. About how suitable, which is today we just implement those things for the real ECG signals. Okay, so in order to do that, usually what we should do is just basically this is the code from last time. This is the ECG data reader that was uploaded to Blackboard for basically with the data set of this research problem. Just share. So basically we're going to be ECG data readers, and then we basically take some code, we just copy some code from here where we computed some features, these features for the ECG datasets. Okay, so basically this is the ECG data reader. Let me run it again here. Basically it is just each one of the ECG types, resampling of the ventricular fibrillation. We will leave the ventricular fibrillation signal, we'll just focus on these types. Basically, system that can discriminate between the normal and each one of the different pathologies. Okay, so basically it's normal versus ventricular copit, or normal versus ventricular bigamy, ventricular tachycardia, or normal versus ventricular fibrillation. .mat. Okay, so basically what I'm going to do is I think what we should do be just things. Okay, here I read the data. Let me clear all here so that you see exactly what we have. Run it again so that you I don't want to save it this way, so save it as basically ECG lecture 1. Okay, but lecture 8 so that we know that this is for lecture 8. Basically, I'm just going to, okay. This data set, this .mat signals from each one of the following types: normal, ventricular. Okay. So this is what we have. So basically, in order for us to start, maybe what we can do is we basically have design in NSIG, okay, and basically this is the learning data, by the way. So basically we're just going to call it NSIG learn so that we know that this is the learning data. We have other data that is testing. Testing should not be involved in any part of should not see the testing data before we actually everything here from the learning data set. So the learning data set here will be basically when we first learn data 1. Basically it's learn data, it's 256 times 1080. 1080 is the length of the signal. 256 is the number of signals. The first 64 of these are basically the normal signals. So basically here, I'm going to define the normal signal, normal data set as learn of 1 to 64 and all. How about the abnormal? I'm going to call it A. Actually, we should design the asig learn to actually take any one of the maybe just have a variable called abnormal type. One is equal to, for example, V couplets. Two is equal to V tachycardia. 3 is for Gemini. Okay, let's start with 1, for example. And basically, in order for us to do that, basic learn will be basically, I'm going to start here from 65. Okay, if it's number 1, then it starts from 65. So basically, I'm going to have this as 64 times plus 64. And all. Think about 1, then 1 times 64 plus 1 is 65. So basically here 1 to 64 is for normal. If I put here 1, then it will start from 129 to 192. Then if it's 3 here, it's going to be 193 to 256. So basically it will select basically the type of signal or the signals corresponding to that particular type. Would like to change between different abnormalities without having to change the code. I don't and basically we change the system between a classification system for normal versus ventricular couplet into a system of normal versus ventricular tachycardia, for example. Okay, so when we do that, let us see these variables. We run these. Are these a problem? 64. Okay, it's not recognized. I'm basic. Actually, okay, I'm sorry. Actually, I did it incorrectly here. Basically, this should be the basic learn is equal to learn data 1 of this variable. These are the ones containing the. So basically, now we have nSigLearn has 64 times 1080, 64 signals of 1080 or 1080 samples per signal, and the ASigLearn has 64 times 1080, basically points per features. Let's start with very simple features. Just start with the mean and the last time. The first dimension. So basically here, if I have 64 by 1080, it will give me basically the mean over the 64, which is not what I want. I would like to have the mean over each signal. So basically I have to do it like exactly what we did last time, is basically just have the mean of this variable transposed, so that it can be basically the mean over 1080. So basically if I have mean of n sig learn, it will give me an array. If I just keep it like this, it will give me an array of 1080, length 1080. This doesn't make sense. This is column 1080. I don't want that. What I want is a mean for each signal. So basically this will happen when I actually have the mean of n sig learn dash. Okay, or basically transpose. This is actually the sign for transpose in MATLAB. So I'm going to do that. Basically, I'm going to say here, so let's say that M1 is equal to, let's call it Mn, so that it's basically mean for N, okay? Or basically we can say that it's feature 1, N, okay? So it's feature 1, so that it can be clear, okay? And I'm going to say here that it's going to be mean. Okay? It will be mean of basically this variable right there. And transpose so that I can get whatever I want, okay? I'm going to repeat that for the abnormal. So just put here a sig learn dash. And basically, in order for me to be able to see whether this particular feature will be useful or not, basically, I'm going to look at the code that we did last time. We had actually a figure here showing basically how the features look like. So I'm just gonna copy that so that I can actually look at whatever came out of the features. Basically, NS here, number of signals, it's clearly equal to, NS is equal to 64 here, okay? So basically, let's have this as figure 1, and maybe just, we don't need to have multiple figures here so far. And here is going to be feet 1, N, and this one, other one is feet 1A, and this should be it. To be able to see how these values look like. Okay, because this figure was already there, maybe I'll close all first, so that each time it draws from new figures. How do you think of that? The circles are for the, let me check. Basically, the X's are for the normal and the O's are for the abnormal. Do you think you can separate them here? Not really sure. It's very difficult to see, actually. How can we make sure? The thing that we did last time was to use the t-test in order for us to be able to do that. We're going to do that right now. So go back here, and the hypothesis testing here will be basically just, have H and P equal to the first and the second variables. Okay, like here, for example, like testing for the mean 1 and mean 2, for example. So basically, I'm going to put that here. So to do that, basically, I'm going to come up with the p-value and the hypothesis. Here, I should put the features, feats 1, n, and feats 1a. That's it. And basically, maybe I can just, okay, we'll just leave it like this and see how these values will come out like. How about this? H is equal to 1 and P is equal to 6.408 times 10 to the minus 6, very small value. So do you think this is okay or not? This particular feature will be useful or not? Based on what we talked about last time. If you remember from last time, the p-value corresponded to the probability that the two features, the two sets of features for the normal, for the two classes, the normal and the abnormal, are exactly the same. So basically, the null hypothesis is that I cannot discriminate using this feature. The one hypothesis, the H1 hypothesis, means that basically the probability of these two features coming from the same distribution, or that the feature is not useful, is very small. So this means that when p-value is very small, what we talked about last time is when p-value is less than 0.05 in particular, we said that we can consider this feature to be useful or significant, or basically has a difference that corresponds to the difference in class. So basically here, apparently it has. It is actually, basically the hypothesis testing told us the hypothesis H1 is the correct one, which means that the two classes are clearly different from each other through this feature. So this is a useful feature. You understand that? Do you follow that?
Yes, sir.
Okay. So the first feature we had is useful, okay? Let's try another one. Basically, we would like to accumulate the features. Basically, I'm going to basically compute several features. For example, now I'm going to add a standard deviation. Okay, standard deviation is computed as basically very similar here. Basically, it's SDD. I'm keep it for now as feature 1 so that I can test it right away from here. Okay, and then I'm going to combine all of them and show you a way to compute the p-value for all of them. Okay, so basically, if I do that and run it, this is standard deviation. Looks like this. Okay, so if we look at the p-value, actually it's very small. So basically, it appears that this is a useful feature as well. Just a standard deviation, a regular standard deviation. Okay, so this is also a useful feature. Okay, so let's compute another. Okay, we actually did last time a few modifications for these two. Basically, we had the difference, which is basically the derivative of the signal, and basically we took the mean of the derivative. We took the standard deviation of the derivative, and we also took here, for this particular part, we took actually the absolute value of the derivative, and we took the mean. So basically we had absolute value here, this place here, right there. What I'm going to do is to have all the combinations as separate features and test each one of them separately, okay? And then combine all of them, okay? Let's try with the difference, just with the difference. So basically, I'm sorry, go back. So basically, I'm just gonna copy that, sorry, the parts here. So basically, I'm just gonna copy both of them. Actually, I didn't draw the other one. Just have this here. I didn't draw the standard deviation so that you can see it. Let me draw it first, and then basically it's going to draw in the figure 1, and it's going to draw the very last feature that we have. This is a standard deviation. It looks a little bit different from the mean, but actually here you can see that the x's are kind of below, and the circles are kind of up, which is actually very clear. It looks very clear. Basically, you can put a line right there, and it would be actually a very good separator between these two classes. So basically, this is rightfully a good feature, actually. It has the ability to separate. So now I'm going to take this one here, and let's put this here as the mean value of a derivative each signal. I'm just going to put here diff. Basically, any particular or any idea you have for a feature, you can just implement it and test it. And look if it's useful, the p-value here will tell you that. Okay, that's it. Very simple. Okay, you don't have to think about it too much. Some people actually try to think about a feature to just try to make sure that this feature will be useful before they implement it. Don't do that. Basically, this area, because you have different data, and basically it's very difficult sometimes to understand what the data has. Basically, you have to actually implement and see how the feature will basically play out with your data. Okay, so basically, this is a different type. This is a mean value of the derivative of each signal. Let's see how this looks like. How do you like that? Actually, this doesn't look so good because actually you see the crosses are in the middle and the circles are around it from both sides. So I don't expect this to be a good feature. Let's see the p-value. Actually, the p-value is really bad. So basically here it's H0. So this feature is not useful. Okay, it's not useful, just not useful. Okay, so basic H is 0, meaning that the null hypothesis is the 1. And the p-value here is really large. It's much larger than 0.05. It's actually here 0.5. So basically this is not a good feature. I'm going to keep it and basically continue on and just repeat this feature with the absolute value. See if it makes a difference. So because basically what we said was that the derivative actually has positives and negatives, and when we take the mean value for positives and negatives, usually it cancels out. So I'm going to have this absolute value of the derivative of each signal. Okay, so I'm just gonna come here and add absolute value before I take the mean. Does this look better? I think it looks a little bit better because at least you see the circles up and the crosses or the x's down. So basically it might be a little bit better. Here, actually it's better, definitely. Yes. See here, it doesn't have to have complete separation as long as you see a trend. Basically, if you look at it and you see most of the circles up and most of the axis down, then this might be a good feature. So actually this is a good feature. Okay, so we're going to repeat that for the standard deviation value of the derivative, no, the standard deviation of the derivative of each signal. Basically, I'm just going to replace the mean here with STD, standard deviation. Please try to understand how I do this because I'm going to ask you to develop one new feature. So in order for you to develop a new feature and assess whether it's useful or not, you have to basically do whatever I'm doing here. Okay, so I'm going to ask you to add a feature that wasn't developed in the lecture and basically test it. I'm not going to ask you to develop a feature that is working. No, I would like you to have a feature and test it and tell me whether this is okay or not. Okay, because if you do that, I know that if you try several features, one of them at least will be useful. So basically, as long as you know how to discriminate between useful and useless features, you'll be fine. So now I have the standard deviation, and basically I'm going to see whether that will work or not. From that figure, do you think it will work or not?
No, I don't think.
Actually, it's kind of, yes, it's kind of mixture, and usually it shouldn't be like that. But actually, at least in this part, you have many x's. Actually, it's very strange that there are x's here and x's there. It's confusing. So I'm not sure actually how it comes out like. Actually, it didn't work. Right, you are right. Okay, so H0 means that it wasn't useful. Okay, so basically, as long as it's not useful, basically we should remove it. But actually, I'm gonna keep all of them. We're gonna keep doing that. Let's propose other features. What other features can we extract from a signal? Tell me if you look at a signal, what are the characteristics of the signal that you can use basically to characterize the features of the signal? Just think about the simplest thing you can think of.
Amplitude, maybe?
Amplitude, yes. The amplitude is what? The maximum?
Maximum.
Right? Right. How about if the signal like the ECG signal, it doesn't have, basically amplitude is usually used for sinusoidal signals. Okay, so basically let's go notes here and discuss it a little bit further. So basically for a sinusoidal signal, basically a signal that looks like this is definitely the amplitude. And the amplitude is usually basically this distance here is exactly the same as this distance here, but actually for ECG, looks like this. Okay, draw it a little bit better. Okay. So basically, usually the levels of the signal are not exactly the same. So what kind of feature you would like to have? Basically, I would like to see this point. How high is this point? So basically, it's the maximum point. I might also want to see this point, which is the minimum point. I already saw the average, the mean. What else can I have? I might think about basically the maximum minus minimum. I would like to see the range. I call a feature the range. Okay, so maximum is an additional feature, minimum is an additional feature, the range is a different feature. How about if we, because actually sometimes the amplification might be a little bit off, and basically for different signals might be a problem because of that. Maybe we can just have a feature as the range over the mean. So that basically I can normalize. So basically I would like to see how much variation is going on basically around the mean. How about that? How about if we add also, because we discussed the mean before, we actually, the median is a better estimate for some cases. Basic median is basically when you sort the signal and basically take the value in the middle of the values within the signal, it's actually sometimes a better estimate than mean, sometimes. So the median is also there. What else? How about if we take the Fourier transformation, the spectrum of the signal? The Fourier spectrum. Fourier spectrum, basically, if I take the signal and convert it to Fourier domain, using FFT like what we did before, basically each one of the frequencies would be actually a feature. Because I would expect if we have tachycardia meaning that the heart rate is really much higher than the usual, okay? And sometimes you have a distortion in the signal. When you have a rate that is much higher, it means that the signal has higher frequencies. So if you look at the spectrum, you will see that most of the energy in the spectrum will be basically shifted to higher frequency in the tachycardia case, for example. So the spectrum will be okay. So these kinds of signal or these kinds of features actually are called transform domain features. Here I'm talking about time domain features. Okay, so we can think about so many things like this and basically try to implement them and see whether they work or not. Okay, let's start with these. Okay, we need to compute the maximum. We should consider each one of these as a separate feature. So I'm going to consider the maximum as a feature, the minimum as a feature, the range as a feature, the range over the mean as a feature, and so on. Let's do that. You understand what we're going to do? We're just going to compute these very simple features from each signal, just exactly the way we did it with the other ones. Okay? Let's start with the maximum. If you have any questions, please let me know. Let me stop and ask me to go back if you want to. Maximum. Okay? So it's very easy now. It's basically, I'm just going to copy basically this here and just instead of the mean, I'm going to have the max. The max also will work on the first dimension, so basically it should work exactly the same way as the mean. So this should give me exactly the same results as the mean, basically. From the point of view of how this function works. So let's try it. So this is the maximum here. Okay. Maximum here you'll have the reds are there, the blues are there. Do you expect this to be useful from this graph? Let's see. Actually, it is useful. The maximum seems to be useful. How about if we try exactly the same thing with the minimum? This looks very good, actually. This is actually one of the best features that we had actually so far. You have so many axes above and so many below. So this should be a very good feature. Actually, it is a very good feature. It is a very good feature. See that the process, how the process goes. At the end, we're going to collect all of these and basically remove the ones that didn't give us good results and basically keep the ones that have separation and basically get started from there on the classification task. Okay? The classification task is basically how to design a surface that would separate these two classes with minimum error. Okay, we're going to talk about it after we finish this feature extraction and selection test. Okay, so now we have, we'd like to have the range. I'm just going to copy it. Maybe I can just have the original one here. Maximum minus minimum, which is the range. Okay, so basically I'm going just to repeat these. Okay, not here. So basically here the feature is the maximum or minus the minimum for each one of these. Here is the N sig and here is the A sig, and let's see how this looks like. Looks okay also. Most of the data points above are circles and most of the data below are X's. So yes, it is. If you notice that the p-value here is even smaller than the two of them. So this is good actually. So basically the range is a better feature than each one of them. Basically, the smaller the p-value gets, the better the feature should be. So basically, when you took the difference between the two, you came up with a feature that is better than either of them. Okay. I'm gonna try that with the normalized range. So basically, I'm just gonna copy that. Say that normalized range is equal to maximum minus minimum over mean. This is exactly what I'm going to do. So I'm going to divide by the mean. We'll just get it from there. Is that correct? If I do it like this? Can you answer me? Would that be correct if I do it like this? Should I put dot here or should I leave it like this? Actually, what we have here, what we get out of this is going to be like 64 by 1. It's a vector. It's not a single value. And actually, the mean here was also a vector. So this is a problem. When I divide two vectors, it's not going to work. I have to have element-wise division. So I have to have dot divide here so that I can have element-wise division rather than regular division. Regular division actually doesn't work if I have vectors. So let's see that. Let's see if the normalized range is good or not. You have some outliers, but actually there is a really nice separation between the X's and the O's, and it's very obvious actually. And actually here it's also there. It's so basically it's not bad. I'm not sure exactly why it's smaller. The p-value is smaller, but actually maybe because of the overlaps here. There are some overlaps here. And there are some X's here, so maybe some errors here, but actually this is not a bad feature. It's definitely a good feature. Okay. So now we computed how many features computed. Do we have any other features to compute? I think these, maybe the median also, we can have the median as well. Median is easier if we take this. So I'm going to have the median. I think the median is just median. Let me check. Yes. So let's try that. Try if the median is a good feature. How do you like it? You know, the general impression is that the circles are up. There are a few of these down here, but actually there's some overlap here, so it's a mixed result. Actually, I'm not sure if it will work or not. Actually, it works. Apparently, it works. Maybe because the general impression is that we have the circles up and the axis down, so basically it came out like this. So basically it should work. So now we have how many features? We have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 features. 10 features out of very simple statistical, statistical computation. Very, very simple. Okay, so basically we can actually have some more statistical features from each one of these signals. I think I'm not sure if it's available in MATLAB or not. Let me see. Cortosis. Yes, there's cortosis not found. Yes, it's cortosis. Okay, this is one of the high dimensional features. Okay, so and basically we have something called the moment. Okay, with something called skewness. These are all statistical features, just like the mean and the standard deviation. For the Gaussian distributions, the cortosis and the skewness should be actually very much near zero. Okay, so if you have something that has a deviation from the normal distribution, you can use these statistical features to characterize how this will work. Okay, how this will be basically how far they are from the regular normal distribution. Okay, so basically it's cortosis for a vector input. K is the fourth central moment. Moment is basically, if you can imagine, the mean is basically the first moment of the signal, the zeroth moment of the signal actually. The standard deviation is the second central moment of the signal. So basically, each one of the statistical features we compute are moments. Okay, so maybe you can just include that as well and see if it works or not. So I'm going to add that. So cortosis. Let's see if it works. How do you like that? Looks very good, right? It's actually very good because actually most of the signals here, the circles are down, and actually some of the signals have very wide separation. This is actually very good. So definitely it looks like that here from the p-value. Basically, I'm trying to compare the figure with the data points to the p-value so that you can understand how we can use the p-value without looking at the figure. Sometimes when you have a very large data set, like what we're going to see right now from the Fourier transform, when we compute the Fourier transform, we will have basically at least maybe half of 1080. So basically, there's going to be more than 500 features. How are you going to do that for each one of them? We're going to look at the figure for each one of them to select which ones are good or which ones are bad. Sometimes it's very difficult. So what we're going to do is just do that just by looking at the p-value. But actually, it's very good useful usually to just get the mental picture of how the separation looks like before we rely on the numerical values. So let's try the skewness. You can just go back here and look at the skewness. The skewness is basically for an input is the third central moment. The other one is the fourth. Okay, so basically we have the first as the mean, the second as the standard deviation, and basically the third would be the skewness, the fourth would be the cortosis. So we're going to use exactly the same syntax here. Yes. Actually look in MATLAB about statistical features or statistical measures, or basically just get the help for mean or standard deviation and look at the other functions that will come out when you see the C also, that part, the C also part here. You will see so many different things, and you can actually, when you get the help for that, maybe I can get the documentation here. MATLAB documentation, you will find some more help actually on how to use them. And you might want to see here the statistics and machine learning toolbox. You will find other functions that might be useful for you to use. I'm suggesting those because you're going to have to do that yourself. So the moment also is one of the things that you might consider also. We're going to try to get together right now. Let's just do the students first. So the kurtosis and the skewness are like the mean and the standard deviation, but they are called higher order statistics. So basically, let me write this terminology down for you. Basically, when we talk about the mean and standard deviation, basically they are sufficient, or basically you don't need any further information if you have normal distribution or Gaussian distribution. The data belongs to the Gaussian distribution. If not, we use higher order statistics. Okay, like for the third order, third central moment, which is a skewness, and the fourth central moment is the kurtosis. But remember this word here, this key word here, higher order statistics, which is basically one of the things that were actually very hot in the maybe early 2000s, maybe the first 10 years of 2000, maybe. People started looking at the higher order statistics and basically adopted as we gave it a higher order statistics. You will find so many papers actually applying higher order statistics, because basically people found out that most of the data they are dealing with do not have a normal distribution or a Gaussian distribution. They have deviations from the Gaussian distribution. And such deviations actually are very key to the process of identifying them or discriminating between them. So actually they found that the higher order statistics are very useful. So basically, if you want to have any moment, basically use the function moment in MATLAB. Okay, we're going to try it now. Okay, so let's see the skewness. We already did that here. Let's see how it looks like. Is that useful? Well, it seems like useful. Basically, most of the data are separate here, so it should be useful. Yes, it is useful. Okay, let's see the moment, the function moment here. So let's see the help so that it can be clearer. So all you have to do is just put the data and put the order. The order here, basically, if you want to have the first order, the second order, the second, whatever, basically you just select whatever you want. So basically, if I say the third here, you will come up with the third order moment. Okay, so basically this is the third order moment right there. Okay, so basically this should be actually the skewness. Okay, if I put basically I have 1, 2, 3, 4 from my features right now. So if I wanted to get more, if I wanted to get the fifth order feature, then I can do that. Okay, and sometimes you can actually have, if you have multidimensional data, you can also have moments in 2 dimensions, but actually don't worry about that for now. Okay, so for the moment here, we can add the fifth order moment, for example. Okay, so what I can do basically is just do that. So I'm going to try the fifth order moment, fifth order central moment. So I'm going to have here a moment and clear 5. So I wanted to have the 5th order moment. By the way, I'm not sure if you know the definition of moments. Let me put the definition of moments for you so that you understand them. Basically, the definition of moment is, by definition, basically the expected value of, let's just call the variable, our variable x, minus mean x, the mean of x, to the power, maybe say nth central moment to the power n, like this. This amounts to basically, if you have continuous distributions, it's basically from minus infinity to infinity, x minus mx. X is definitely a vector or a function, basically, the power n times probability of x, the probability distribution of x, dx. If you're talking about discrete, this is for continuous variables, continuous distributions. For a discrete distribution, like what we have discrete data. We don't have data that are basic continuous. We have data that are discrete. So basic is going to be like x minus mx to the power n times here. The probability here is replaced by the histogram, because the histogram actually is an estimate of the probability distribution. Okay, so basically you do it like this. This is basically the probability here. And this is basically, and you just compute basically over n. If you have a number of points, all points. Okay. You don't have to worry about how to implement this function, but actually it's implemented like that inside MATLAB. So let's see if this function will be useful or not. Kind of very unusual. You have very, have points here that are really far away, and the points here are kind of mixed together. I'm not sure, they are not very separate from each other. Let's see. Actually, it's not good. So it gave us a value that is higher than 0.05. It's about almost 0.2. So basically, it's not very useful. So basically, apparently, it's enough to have the 3rd and the 4th moments. Any moments beyond that will not be very useful. Okay. Is that clear? Is it clear to you how to think about a feature and how to go about implementing and testing it?
Yes.
Is it clear to you?
Yes, totally.
Okay, so now what I would like to have, basically I computed several features. Maybe now after I added, maybe I added 3 here, maybe I have 13 features here now. Okay. What I would like to have is, I'd like to have all the features combined together. So basically what I would like to have is, I would like to combine my data to look like this, the following. Basically, I have to have an array that looks like this. And basically, I would like to have either the columns or the rows. Let me see here what this looks like. Feature 1A is 1 by 64. So basically, each one of these is a feature. So basically, I'd like to have each row is basically a feature, and each column is a case. 64. Okay, so basically here, these are cases, different cases, and here these are different features for each case. I'd like to have them. What we have right now is this column right there. Basically, I have this column right there. Okay, I have this row right there. Okay, more it a little bit better. So basically, I have basically a features. Basically, I have these values. No feature. What I would like to do is basically compute each one of the features and basically combine them together in one variable. I don't want to define the variable at the beginning because I don't know exactly how many features they have. Okay, so basically what I'm going to do is whenever I compute a feature that is 1 by 64 and another like feature 2, 1 by 64, I would like to add these together, combine them to be 2 by 64. How can I do that? How can I combine them? From the basics of MATLAB. Let me try it for you on MATLAB and basically come here. Basically, I just have x is equal to 1 to 5. Y is equal to, for example, maybe 10 to 15. Okay. So basically, I think these are different dimensions. So just have this as 11, 15. So basically, x and y, basically, if you look at them, they have basically dimensions of 1 and 5. 1 and 5. Okay. How can I combine them? Basically, if I say x comma y, we'll add them together with the same dimension. Basically, the first dimension will keep it constant and add the second dimension. If I add it, if I combine them with semicolon here, we'll do that. Just we're going to consider each one of them as a separate row. So to concatenate the two variables together, okay, so that basically the last one here, the last size, the size of 5 here will remain the same. Let me try that in the code I have right now. So each time I compute feet 1, okay? Let me just say that we have a variable called feet. That's feet, okay? Feet n and feet a. Okay? I'm just gonna make that as an empty array. Not sure if that works, but actually it should work. We'll try it first. It should be okay. Feet 1, it's just an empty array, okay? So now what I'm going to do is whenever I compute a feature, I'm just going to add a single line here. Feet n is equal to feet n semicolon 1 n. This will do what? It will take whatever I have and concatenates the last feature that I computed to them. Okay, so try that. Or the first one. So if I do that, now it's empty, it's an empty array. After I do that, it will have a dimension of 1 and 64. Let's try it. See now, feet A is 164, feet N 164. What I'm going to do in order for me to concatenate or combine, easier terminology, into one array, okay? To common array. Okay. I'm just going to copy that the same way, exactly the same way after each feature. That's it. This will actually concatenate or basically combine all the features as I did in one array. Very simple terminology, very simple code. Run that. Let's look at our variable. Feat A now has 13 by 64. 13 means that I have 13 features combined now together in feat A and feat N. This is actually what I'm going to use later for classification. I have to have all the features in one array. I cannot have the features in basic each feature separately. Okay, I have to actually combine them in one variable because basically I'm going to consider each case as it is defined by the features, defined by 13 features in this case. Okay, each one of the cases is defined by these 13 numbers. If I add more features, then the definition of each case will be basically composed of more features. Okay, but I actually have to have them in this way. Okay, so how can we test it? If we have these features, can we test it directly with t-test? Let me show you something very neat. Okay, I'm going to just use that here. If I put here feat N and feat A, okay, let me see what will come out. See here, what came out of this? But actually now it's actually computing along the 64. So basically, what I should do in order for it to work properly, I'm just going to have to put a transpose so that it does the testing along the other dimension. So now the edges, basically it gave you the results that we computed one by one. It gave it to you directly here, basically as you see here. And here, because actually in MATLAB, the default display of variables is basically abbreviated to 4 decimal points, 4 decimal zeros, basically. So basically anything below basically the 10 to the minus that we were seeing, like the one that we saw before here, the things like that will be just, reported as 0 because these are very small numbers. I can actually change the display, but actually for me, it's actually enough to see it like this. So this is clearly not working. This is clearly not working. This is clearly not working. The other ones are working. How can we remove the features that are not working? We'd like to do some MATLAB, some really nice MATLAB coding, do that in a very short sentence. We would like, basically I can do it manually. Basically, I can check each one separately and basically choose if I select it or remove it. But actually, we can do that in a much easier way. So basically, it's a very nice function that we can use. This is a variable called p. If I say p greater than 0.05, it will come out like this. Basically, if I compare my variable to my array to a number, it will compare each one of the values or each one of the elements of this array to this number and give me a logical array like this. Okay. So basically now for the third one, it came out like 1, which is true. This is greater than 0.05. This is also the fifth one, and the last one are all like this. Okay. Now, if I have this array, basically, if I wanted to remove these columns, okay, remember that our array here, the feat N and the feat A are 13 times 64. I would like to remove the row number 3, the row number 5, and the last row, the row number 13. How can I do that? You know how to remove a row from a matrix? Let me show it to you also as an example, very simple example, okay? Let's just say x is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is a very simple matrix, okay? If I wanted to remove the second row, all I have to do is do the following. Basically, just say x equal, or basically x of, and all is equal to empty. That's it. You know, x of whatever row I would like to remove, and all is equal to empty. I can actually remove also a column if I want to. Basically, I can do the same thing. Basically, if I wanted to remove the third column, for example, I can say the same thing. Here, I remove the third column. We can do the same thing here with our array in a very much the same way if we just say that feet n of p greater than 0.05 is equal to empty. This is a really nice way of doing this. Basically, this will check the p-value array. It has to be p capital, I'm sorry. It's to the p capital array. So it will check the array which actually the values in the p array, the p-value array, and basically for each one of the values that has a value greater than 0.05, it will remove the column from feature n. So basically, I'm just going to try that. Sorry. Okay. So basically, it did that. Okay. Let me try now. Maybe I'll just do that for feature A as well, because basically I have to remove it from both. I cannot have a feature in the normal and not have it in the abnormal, or the other way around. I'm going to try the t-test again. T-test 2. Of n dash and feed a dash. Basically, if I did that correctly, then I should actually have p-values that are zeros for all of them, right? Because actually I removed the features that were not useful. Okay. Okay, I didn't. Okay, feature n. Okay, there's something wrong here. Something went wrong here. Oh, okay, sorry. What I did here was basically I did that for p equals b greater than this, but actually I should have like this, like a semicolon. I have to have actually the rows only. Basically, it combined the array into one function. So let's do that in the code, because actually we have to compute these again. So here I'm going to compute this, and then have feature n and feature a of these. I have to just add this. The missing part was this. And I'm going to test again. Okay. And see what happens. Okay. See now? The the first one had these values. These are very small values, you can see. Basically, this is 10 to the minus 3. So all of these actually have very small values. And here, basically, if you look at the p-values here, we have 1, 2, 3 values that are above 0.05. The result for each here was 1, 2, 3, 4. We have 13 values here. If you count these, you will find that they are 10. The 3 values were actually removed. The 3 values that are higher than 0.05 were just removed. So basically, this will make it much easier for me to add features and basically test these features and just remove them without actually having to think about which ones are the ones that are removed. Okay, I don't have to test them one by one and basically remove one by one. Okay, I can actually test them all at the same time and remove all at the same time. Okay, is that clear? Very simple code.
Yes.
Have any questions?
No, it's clear.
Okay, now we're going to actually see how that will be useful when we try to add features from the Fourier transform. Okay, let's go back to the drawing board. Basically, this is what we did here. So basically, we did that already. Okay, we combined them. Okay, using basically each one semicolon. Okay, and basically we did that and came up with an array of, let's just call it feature array. It is like features here, and here cases. Okay, just clarify this. So okay, so we enter that into the t-test. Okay, and basically removed useless features. Okay, okay, so now for example, if you consider this as NF and this is NS, number of samples. Okay, so basically we will come out here like it has to be NS also and NF dash, and NF dash must be less than or equal to NF. You cannot have more features here after testing. You either keep them all or remove some of them. So basically NF dash should be less than or equal to NF. Okay. Now what we're going to do is compute the Fourier transform. For the Fourier transform features, basically, as we said before, if we have for each one of the cases, we have an array of 80 samples. Okay, when we do the Fourier transform, what is the length of the vector coming out of here? From what we saw before. What is the length of this vector? Will come out as 1080, as we said before. Basically, this was what we did before. The DFT will basically take n here and give you n here. Okay, and the n here will be complex numbers. So basically, we have to take the absolute value because actually the phase here is very complicated. So basically, we take the absolute value of that. So I end up with 1080. But we have to notice a few very important things. Is that the spectrum, because actually we have real values here, we will have asymmetric spectrum here. So as we saw before, if we have something that whatever looks like whatever here, so it look like this here. So basically, this is equal to exactly like this. So basically, if we take the whole thing, basically we will have each one of these values will be double. The value here will be exactly the same as here, here same exactly as here. So what I should do is just take basically half the data. Okay, so basically symmetry will mean that redundancy, redundant features, meaning that we have repeated features. So the solution to that is take half. Take one of these, basically if the features look like this, for example, take this and remove that, because basically they are the same. This is the first thing. Second is related to the complex variable that we talked about. We have complex data. The phase, as we saw, is really complicated, looks very complicated, actually. We don't look at the, usually when you look at the Fourier transform, we are more interested in the energy in each one of the frequencies. So the energy is related to the absolute value, the magnitude of the complex data, rather than the phase. So basically we take the absolute value in order for us to be able to do that. The third thing related to the Fourier transform is how many points. Basically, we have been working for an hour now, maybe more than an hour, to come up with 13 features. Now, if we do the Fourier transform, we will end up, even if we take half, we will have more than 500 new features just from the Fourier transform. It doesn't make sense. Basically, you don't expect to have that many features to be useful. We can test them all as we did before, as we did with the other features. But actually, because of the noise, because of the very subtle variations between normals and within normals and within abnormals, it doesn't make sense to have frequency resolution that much. So basically, there is a way in Fourier transform, the average into bands. Meaning that if I take the Fourier transformation, instead of taking basically if I have, for example, 1080 points, instead of coming here as 1080, no, I'm going to basically have each 4 points, for example, or each 8 points, or even each 16 points, basically combined. This will basically give you a spectrum, if I'm looking only at the positive spectrum, basically as if I'm computing the energy in each one of these bands together. So basically this band has many points, this has many points, this has many points. I'm computing each band, okay, the energy within each band, so that if I have a small variation here within that band, it wouldn't really matter. This actually will also make the noise within each one of the values of the Fourier spectrum a little bit lower. So basically this actually can be very useful. So there is a very nice feature in MATLAB. You have FFT. Basically, if X is your vector, basically you add N here. And N here can be smaller or even larger than the original. X capital here is equal to this. So basically, if I have 1080, I can decide that I would like to have only 10 features, for example, or 20 features, whatever. I can put N here, whatever I want. Let's try that. Let's try and see how that works. Okay, let me just take one of the signals. Here, asig learn, I'm just gonna take one of them. X is equal to n sig learn of 1 and all. Okay, so X now has 20, okay, in 80 points. I'm going to have X capital is equal to FFT of, let's just have absolute value so that we can have, as we said before, X, and I'm going to have like 20 here, okay? Maybe I'll make it as 21. I'll tell you why in a second, okay? if I do it this way, we find that capital X now, the Fourier transformation of X will come out now like 21 points. These 21 points are basically, I'm taking the 1080 and averaging bands so that they come up like 21 bands within this range. So I divided the 1080 into 21 bands, and basically what comes out is the 21 bands, the average of each one of the bands. Let's look at the values. Let's see how X looks like. If you look at this here, first of all, the first point always is the DC value. Basically, you have to keep that. The DC value, by the way, will exactly be the mean. Will be exactly the mean value. Okay. Here, 0.0242. Here, it's 0.0242. 0.00441. 0.0041. Because basically, as you remember, for the Fourier transformation, the FFT, what it does is it gives you the spectrum. It gives you a spectrum that looks like this. Okay, remember? Basically, this is from 0.0 to n-1, for example. Basically, it should look like this, but actually it gives you from 0 to twice pi, not from minus pi to pi. Okay, so basically what you will see that the DC value is different, and then each one of these values will correspond to another one from here. Okay, so this one will correspond to this one here, and so on. Okay, so basically if you look at it here, look at the values here, if we have 21 points, we will have only 11 out of these 21 points that are useful. The other ones will be copy of them, basically. See these values here? First 11 values here. You will see that the values will start repeating afterwards. 0.0312, 0.0312, 0.0057, 0.0057, and so on and so forth. So now we can actually take the same exact idea and implement it here. Okay? So basically I'm going to add now, just make it a little bit larger here. Create transform domain features. Start with the Fourier spectrum. So I'm going to maybe copy one of these. Actually, now we cannot draw because actually I have so many features. So basically, I'm just going to comment out the drawing here. It doesn't make sense. And then we're going to have these like this. Now we're going to have here, this is as the FFT. And maybe have the absolute value as well. Let's start with, or basically have the number of points or number of bands as a variable. So basically, I'll just have it here as 21. Okay. So basically, maybe I can have. Yes, that's fine. And basically, absolute value of this and bands should be okay. Should be okay. Click here. Okay. And bands. Basic. A very useful thing, actually, if we want to know the number of useful features, I can do it this way. In useful equal to sum of p greater than 0.05. Now, what I did, basically the p greater than 0.05 will give me 1, like what we did here, will give me 1 for each one of the not sure, yes, it's probably here. Yes, something like this. Basically give me 1 for each one of the features that did not meet that criteria, the criteria of 0.05. Here I should have it as less than or equal to 0.05. So basically this will give me the value of useful features here, number of useful features. Okay, so now what I did was to compute the spectra here, and actually I should have a little bit of modification because I have to select only the first half. So I'm going to have it like this, of n of 1 to n bands over 2 plus 1, and I'm going to round that. Let me check it first. Okay, so I don't need to, just gonna have it here round. I'm just gonna pick the first half that we just saw, the first unique set of values, and basically just put them in feature N and feature A. Okay. Let's see how that works. There's a problem here. Vector cat. Okay. Let's see. Feature 1 now is 1 by 11. Okay. 13, feature A, feature 1n, and feature, okay, there's a problem here. Actually, the Fourier transformation didn't understand. Maybe I'm not sure if the Fourier transformation will actually be possible to have as a vector here. Let me see. See? The vector X for matrices, if we apply to column, it's applied to each column for n dimensional arrays. Okay, I understand now. So basically here, instead of doing that, in the part where I actually remove the points, where that is. Yes, here. Basically, I should have only the, let me just compute these first and show it to you here. Basically, it comes out like 21 times 64. So basically what I did here was the mistake that I made before. I basically just put this. I should actually have this and all. So basically, I'm selecting the features. I'm selecting just the first 11 features with all cases. Okay, so basically this should work now. Okay, didn't work. Unrecognized. Round is not recognized. Okay. So basically this all is not correct. I should actually move the to be okay, hopefully. Just a matter of parentheses. Okay, it worked. So now the p-values, the number of useful values are 11. Okay, apparently the basically the features that we added 11 features. We have now 24. If you see that, the last few actually, if you see here, the number of useful features after everything was like 11. Okay, what we had from before, we had 13 values. That we removed 3, there were like 10 useful features. Now we have only one feature that came out. This feature is actually this one here. This is the only one that was useful from the Fourier transformation. So basically what I can do probably is try to change the number of bands, because basically maybe it's too small. You just have 51. Let's see if it made any difference. So now the number of useful features is 30, which is really good. Now I came up with more useful features. This is good. Okay, so as you see here, the number of bands, the way I divide the bands will make a lot of difference, because basically if you have variations between the different classes, And these variations will result in shift in the frequency domain, shift in the frequencies of the signal. Then I better have more bands so that I can discriminate between the different variations in the signal. Okay, and basically this will depend on the kind of abnormality that I'm using. Here I tried the ventricular couplet. Let me try the ventricular tachycardia and see what happens. The same exact features will be computed for the different type of abnormality. Let me see here how many features we can come up with. Actually, it came up like 30 also, which is good, which is not bad. So if we change that to 3. Now it's 34. So basically, you would expect the number of useful features to change with a different problem that you're trying to classify. So for example, if I'm trying to classify normal versus a particular pathology, the features that will come out like useful might be different from the ones that come out as useful for another pathology. Okay, and the count will be different, might be different, might be the same, but it might be different. But in each case, we cannot use the same classification or the same classifier for both. I have to design a classifier for normal versus pathology 1, and another classifier or another system for normal versus pathology 2, which makes sense. Otherwise, it's basically all pathologies are the same, basically. I don't have to discriminate between the pathologies, different pathologies. Okay? So basically, this is the general idea about what we do for feature extraction and feature selection. What we do here is try to propose different statistical measures. As we said last time, as we looked at the different cases last time, there are different variations, there are wide variations within each class. If you look at the normal cases, and within the normal cases, you will find differences between different people. Within the abnormal cases, for a certain pathology, you will find also differences for each one of the cases, for the different individuals within the same class. So that's why we'll try to come up with features that describe the whole signal and try to hopefully find some of the features that can capture the actual differences or the main variation that happen between the different classes, so that we can basically use them to identify these signals. Is the idea clear?
Yes.
Okay, so what you will be asked to do in research problem 2 is basically to design a system. And the first part of designing a system is to design the part about the feature extraction, and basically with the feature extraction comes the feature selection. We talked about a very simple feature selection, which is basically the t-test, the statistical testing. Next time, inshallah, I'm going to talk to you about a more advanced kind of feature selection, and hopefully, inshallah, we can get started on the idea of classifiers, how we can design classifiers. Okay? The basic idea of classification is whenever we have a system that looks like this, whenever to have a data that looks like this, how can we design a surface? Or basically, if I'm talking about a graph like this, how can I design a threshold? Okay. Or if I'm talking about n-dimensional case, if I'm talking about a two-dimensional case, I'm talking about a line. If I'm talking about a three-dimensional case, I'm talking about a plane. Okay, or in general, maybe you can have a surface that has basic variations, not just a plane like a paraboloid or something like that. Okay, if I'm talking about n-dimensional, if I have like 30 features like the one that we have here, right now for this particular problem, we have 34 useful features. So the dimension of the space of features is 34. Okay, it's not one-dimensional, it's not two-dimensional, it's not three-dimensional, it's 34th dimension. Okay, when you have 34 dimensions, there is a problem in even imagining how the surface would look like. So we're talking about hyperplanes, We're talking about hyperparaboloid. We're talking about maybe whatever surface we're going to have. And the design of this surface is the idea, or basically the technique that the classifier is based on. Okay, so the design of classifiers basically is a technique to try to estimate the parameters of a surface of a certain shape so that you can optimize the separation between the two classes. We're going to talk about this next time, inshallah, with more advanced feature selection. Okay? So do you have any questions about what we talked about this time?
Thank you.
Okay, so I think we should stop here because I don't want to give you more, we're not going to go into a new topic at the end of the lecture. So basically, we're going to stop here. And next time, inshallah, we're going to pick up from where we left off. And I would like you to basically try this code and try to basically come up with questions to better understand the process. And it would be great, actually, if we try to propose a feature and try to basically compute it and test it and see whether it works or not. Okay?
Okay.
Okay. So if you don't have any questions, any further questions, then inshallah we will conclude now. Okay?
Thank you, Doctor.
Okay. Do you have any questions about those who didn't submit the assignment? Do you have any questions about the assignment, second assignment? Assignment 2 and assignment 1 are research problem 1, and basically divided the requirements of research problem 1 into assignment 1 and assignment 2. So you don't have to submit anything more than assignment 1 and assignment 2 to satisfy the requirements for research problem 1.
Okay, Doctor. We already submitted.
Yes, okay, that's fine. But I mean, I want to comment on the helping. Okay, you try to help your friend Tariq, right?
Yeah, he worked with.
Okay, what I received from him was your code, okay, with your name on it. Your name was inside the code, okay? So this doesn't make sense, okay? Please, helping is intended to basically show your friend how to do things, okay?
Yeah, okay, Doctor. Exactly. I sent to him the code to see it and change it. And I want him to understand the idea, not copy it and send it to you.
That's fine. But I mean, helping sometimes, people understand helping in different ways. So basically, just make sure that if he has questions, answer his questions. But I don't prefer that you share the code, because sometimes it's very tempting, actually, you have the code to just run it and that's it. Basically, you think that you understood it when you run it, but actually this is not the way you learn about things. Okay? Yeah. I'm not blaming him. Actually, I know that he has a problem with the MATLAB coding and things of that sort. We try to help him all. Basically, we're going to all try to help him. But I mean, helping means, trying to make him do things, or basically understand the things that he doesn't know how to do, things of that sort. Okay?
Clearly, I will call him and we'll discuss with him about that.
That's fine. I actually gave him these comments actually on Blackboard, but I'm not sure if he's not here right now, unfortunately. So that's fine. We're just gonna, I'm just gonna wait for him to contact me if he has any questions.
Okay.
Okay. Thank you all, and see you inshallah next time if you don't have any questions.
Bye.
Okay, Assalamu alaikum.